Hey everybody. So, I was talking to people in the Thursday lab, and I think, so some people expressed confusion about the CNN stuff, and so what I have kind of decided to do is take a little more time. Why did that not work? Take a little more time to talk about CNNs and try to explain some things slowly and consistently that I maybe went over too quick, and then I will do another video later today where I'm going to talk about recurrent neural networks and maybe LSTMs, right? Because those are going to be the next unit probably. And I guess maybe to get a little bit of discussion about where we are, where we're going, and why out of the way. First, I feel like, so CNNs and RNN/LSTMs are two sort of evergreen technologies, right? There are a lot of sort of specialized networks that we could talk about, but these two are extremely common, right? They were both invented, I think, in the 90s. I think Linnet was the 90s, and this, I think, Hochreiter Schmidt-Huber was 90s, which is where the LSTM comes from. And they keep getting used, right? They're still used today in state-of-the-art networks. So I think talking about these two as building blocks of sophisticated networks is super important. And if we can get through both of those and then a little bit of something else, I think we will have done a pretty excellent job for the course, right? So what I'm telling you is if we can get through CNNs with half of this week and then get through, so this week is ambiguous because these are Friday, right? But if we can spend Unit 8, right, and we can kind of go halvesies between CNNs and LSTMs, and then if we can get a Unit 8.1, say, that finishes LSTMs, I think we'll be in a really good place. I think that's a very good place going forward, right? But having said all of that, this is the CNN further explainer because I think a lot of people are still kind of confused, okay? So I think one of the problems is that we have lots of, right, unclear terminology. Good job, me. Why is it? No, let go of the pen. What the? All right. It was a fascinating glitch. Right? I will throw around terms like feature map, right? Feature plane. And kernel, right? And fully connected. And maybe it's not always clear exactly what one of these means in a given context, and it's kind of hard to keep them organized. To some extent, that's just kind of the nature of the beast, right? I know it's a problem when you're, trying to learn this, but it just kind of is the case that all these different terms are relevant, and they all are germane, but they all can mean slightly different things in slightly different contexts. And it is a lot to keep track of. And I think that's just sort of true in the literature at large, right? Like if you pick something like feature plane, right? That's not a term that every author uses, and the authors that do use it can mean a slightly different thing by it, right? And so it is just sort of a bit of added cognitive burden that you have to try to keep track of, okay, what does feature plane mean in this context, right? And if author A describes thing A as a feature plane, do they mean the same as author B talking about thing B, right? And that problem even goes all the way back to the basic idea of a convolutional neural network, right? In that even though I'm kind of talking about what a CNN is, there actually are a bunch of slightly different formulations of this thing, right? I believe it is true that the original sort of Linnet, again, I say original, I think CNNs predate Linnet, right? There's other literature, but this is sort of the defining one, right? I think the way they built Linnet and called, like the thing they called a CNN there, is not the same thing that you get in TensorFlow. It's a little different, all right? And that's just kind of the unfortunate nature of this field, right? Is that it's not very standardized, right? A lot of authors use the same term to mean slightly different things, right? And CNN according to person A is not exactly the same as CNN according to person B. A lot of times I feel like the differences are not worth going over, so I kind of try not to, but I think that some of those subtle problems may have tripped us up this time, right? And so what I'm going to try to do for the next little explainer, I'm going to try to be very precise in my wording, and I'm going to stick to, as much as I can, what I understand the TensorFlow definition of these terms to be, because TensorFlow CNNs are the ones that we're going to be using, obviously, right? Okay, so let's dive into a short re-explainer of TensorFlow Convo-Layers, right? So I guess that's one of the first things, right, is I'm going to try to talk about like Convo-Layers, right? Because saying ConvoNet makes it sound like there's something special about the entire network, whereas as far as TensorFlow is concerned, we're talking about like a specific layer that we can mix with other layers, okay? So here is an explainer of TensorFlow Convo layers. We're going to kind of start with what they're not, right? So we, I hope, have a pretty good understanding of what a dense network looks like, right? When I've been drawing pictures of neural nets before, I think we kind of understand how those work, right? We've got these units, and every one of them, let's talk about this one, is connected to every unit in the output, right? And here, like, I'm omitting a bunch of units, right? I've drawn 6 and 4, but there could be 10,000, right? Where, like, 10,000 minus these 6 are omitted in this ellipsis, okay? But every one of those, you know, whatever, k, units in the input, is connected to every one of the, you know, whatever, j, units in the output, right? That's a densely connected network. And we talked about the problem, right, is that if you imagine these units as being input units that correspond to pixels in an image, right, then each one of, so you have one output unit that is connected to every input unit that is a pixel in the image, right? This output unit, and I'm not going to draw all of them, this output unit, if it wants to learn to locate, so it can't realistically learn to locate a boot anywhere. It has to learn, if we're talking about fashion MNIST, to locate a boot right here, right? And spherical boot. There we go, right? So some pattern of units, if this is the boot in the corner unit, some pattern of weights connects those input units to this output unit, okay? And then everywhere else, it's connected, but those weights probably need to be 0, right? Because otherwise, whatever junk is happening over here could affect the output of the detect boot in a corner unit, right? And the problem is, and now I just realized I've got a whole bunch of circles here, and that's maybe not informative. Here, let's very quickly. Yeah, we'll leave the output unit as circular. We'll make the boot, because I cannot draw a boot, we'll kind of draw it diamond shaped, right? So all of the units in that shape are connected to the diamond in a corner unit, right? And all of the weights connecting the units everywhere else need to have a weight of 0, okay? A weight of 0. And the problem with this scheme is that you then need to have a unit for diamond everywhere, right? So this unit detects diamond up here, and then this unit detects diamond down here. And this is why, and that's obviously infeasible, right? Because you have an explosion in the number of units you need based on where you need to find a diamond. And it gets worse if the diamonds aren't exactly the same shape or the same size, right? And this involves like an explosion in output units, and it involves an explosion in input, because now you need to have, at least one training sample for every location there could be a diamond, right? And every scale there could be a diamond. And that's clearly impractical to do, right? This is why dense nets, so again, this is why dense nets are really terrible at image problems, right? And I kind of want to choose my words very carefully there, because you could use one, right? You could, in theory, define like a 300,000 unit layer and just produce a lot of diamond images and train it, and that result would be mathematically perfectly well defined, right? That would work. It would just be ridiculously inefficient, right? Ineffective. So since we're speaking of terminology, right, this is what you get with a TensorFlow dense layer. TensorFlow kind of calls this dense. A lot of other authors call something like this fully connected, right? Fully connected often defines this because this layer is fully connected to this one, right? All of the connections between this layer to, all of the connections from this layer to this layer exist, right? So dense because there's a bunch of weights, fully connected because all of the connections that could exist are there, right? So now let's look at what a CNN is, okay? A Convo-Layer is. First off, instead of just having sort of a big linear list of units, we kind of logically connect them into, that plane structure, right? Here are some input planes, and then here are some output planes. And I'm going to do sort of 2 to 3. I think a lot of people kind of have an intuition for what we're talking about when there are 3 input planes, because that corresponds to, or I think at least some people have an intuition for what we're talking about when we talk about 3 input planes, because going, oh, that's like red, green, and blue makes sense, but then they get confused when it's not, the red, green, and blue of an image. So I want to skip that by not even talking about that at all, right? Right now we're just going to think in terms of planes, right? Planes to planes, regardless of what kind of planes these are. So just collecting the units into planes wouldn't necessarily change anything, right? We've grouped the units differently, but we could still have a unit right here, right? Well, this unit could still be responsible for detecting a boot at this location in this plane, right? We could group them into planes and densely connect them, right? And then you would have every unit in this plane being connected to every unit in that plane, right? And then every unit in this plane being connected to every unit in that plane, right? So just grouping these into planes and then densely connecting them would be possible, it just wouldn't do anything, right? You'd have the same basic problem, which is that this unit would have to learn to recognize exactly one boot or one diamond. Again, I said I'd be consistent. I'm going to try to be consistent. It'd have to learn to recognize one diamond at one place and then ignore all the input on all the other planes, and that's no bueno, right? You still have the exact same problem. So besides organizing the units into planes, okay, convo layers do something else. They do not fully connect the layer, right? They are not dense. A unit here, instead of being connected to every unit in every input plane, is connected to a specific receptive field, right? Just this patch, right? And then just this patch of this plane. See? So I kind of talked about learning to find a diamond in one place and then zero all the other weights. The convolutional network is basically already built like that, right? A unit in the output plane has a particular geometric interpretation, right? It's connected to a specific region in the input plane, or I should say it's connected to a specific region in each input plane and nowhere else, right? So it's not dense. It's missing a bunch of the connections a fully connected network would have, right? It's connected to a specific receptive field. Okay? So it's not dense, right? Because we don't have all of the connections. It's connected to a specific receptive field, which is just this little patch, right? So that already helps, right? We're closer to the thing that we know that we need to learn, but there's at least one other step that we have to go through here, okay? Right? So now we have gone through, So now we have gone from, let me pick a size for this layer. So actually, I'm going to do this first. Let's label these. This is plane A. This is plane B. So input plane A, input plane B. And then this one is output plane A, output plane B, output plane C. All right? So even though they're connected differently, it's the same kind of weight math, right? Output unit A, right? Output plane unit A uses the same kind of multiply the input unit by a weight math to figure out what its activation is, right? We're going to compute it with the pre-activation equaling the sum over, right? Input plane A, unit I, right? Okay, I'm going to have to move that over a little bit. I don't have enough room, right? Pre-activation equals sum over, right? Input plane A, unit I, times weight to the output A, and I used K for kernel, we'll get to it, I, damn it, I, there we go, right, plus input plane B times kernel B, I, right? And then, just like normal, we apply some nonlinearity to that, okay? So it's the same kind of math where we multiply the units by the weights, we sum them up, and then we apply a nonlinearity. It's just that instead of summing over all of the weights, we're only summing over these little, like the weights in these little receptive fields, which I have here denoted with Ka because we're going to call it a kernel, okay? So instead of summing over the entirety of each plane, we're just summing over this little patch of a plane with this little patch of weights, okay? So I called that kernel A and kernel B, right? Okay, okay. Again, I'm sorry if I trip over myself a little bit. I'm trying to not, I'm thinking we'll jump here. Oh, maybe not. Sorry. So, right, we have, so we're summing over these little regions, right? So this again helps us a lot, right? All right, hold on. So, we'll go here. What do we do with this unit? Well, and I'm going to color it differently in the hopes that we can clearly see what I'm talking about. What do we do with this unit? Well, that unit is going to get a slightly different receptive field that's going to overlap. We're going to slide the receptive field over a little bit so it includes part of the original field and misses part of it. And then we're going to do exactly the same thing, right? Again, if I kind of struggle to draw a straight line, it's because I'm sitting at an angle to the tablet. We should rearrange my desk at some point. So this little unit B, right, or sorry, this little second unit in the output plane, right, is also connected to little receptive fields from input plane A and B. They're just slid over by some amount, right? It might be 1, it might be half width, whatever it is. The TensorFlow one defaults to 1, right? Slides over 1 unit in the little 2D plane and then repeats. So this helps, but there's another kind of, okay, so again, if we're building up to what a ConvoNet is, this is going to help a lot, but there are still some problems, right? Because if we just did it this way and didn't talk about kernels, right, we would have the problem that there's still a bunch of different weights, right? This plane could learn to recognize a diamond with this, with this unit, right? This unit might be looking for a diamond in its receptive field. And then this plane, the green one, might be looking for a square, right? And that kind of doesn't make sense, right? These units aren't related, right? The feature they're looking for is not related. We would kind of like this layer, right, to associate with diamonds, right? We'd like it to be where you found a diamond. And part of the motivation of that is controlling the number of weights. If this unit and this unit get to learn different filters, right, then we have a bunch of different weights involved in, I use the word filter again, I'm sorry. If this unit gets to have very different weight patterns than this unit does, right, then we have a lot of weights to learn, right? We have, so whatever the width of this is, right? So let's call it receptive field width, right? We got a lot of weights to learn. If the plane, oh boy, if the plane is, come on now, pick a color. Where did blue go? All right, there it is, right? Sorry, again, the joys of like not having labels on this keyboard. All right. There we go, finally. So, if the plane is J, or is, let's go width to a side, right? If the plane is plane width to a side, right? And then that little field is field width to a side, right? Oops. We have, in terms of weights, I've made it worse. All right. We can make about field width minus 1 fields, or say PW minus, so plane width minus field width minus 1 fields per side, right? That's what I'm trying to get to, right? Where this is how much we advance, right? Well, I said that, I'm not sure. The math might be different, right? So if we advance by 1, it's this, there, right? And then if this thing is square, right, if the plane height and field height are the same, then we have that thing squared fields per plane. You understand? I feel like I might have just tripped into that a little bit too quickly, right? So what we're talking about is if we break it into receptive fields but don't talk about kernels and filters and that crap, right, and allow the weights to be free, how many weights do we have? Well, we have this many windows, and each window, each receptive field, has field width times field width weights in it, right? So that's potentially a lot, right? That's a big number, right? We wind up with this times this in fields, right? So we wind up with, oh, I wish I had an eraser, right? I might have an eraser, I just don't know what the hotkey for it is, right? We wind up with PW minus FW minus 1 times FW squared unit, squared units, right? And that's a lot. So what we do to reduce the number of weights we have to learn, which also has the convenient effect of making this this plane meaningful as a filter, is we tie them together, right? We say that, okay, this receptive field has to have the exact same pattern of weights, right? This receptive field has to have the exact same pattern of weights that that one does, okay? And that's where we start talking about kernels and filters, right? So not only do we have these tiny receptive fields, but we have the rule that the same little pattern of weights goes in there, right? So this pattern of weights is getting applied here, and then it's getting applied here, right? The weights are tied together to be the same. So it's a little bit tricky because plane A and plane B might contain very different information, right? So we could use the same pattern of weights in plane A and plane B, but that might not be ideal, right? Because they might carry very different information. And so we're going to allow plane B to have its own little grid. Come on now, close enough. Its own little grid of weights, right? So plane B has a little grid of weights that connects each receptive field. Input plane B has its own little grid of weights that connects each receptive field to this region of the output, to this unit of the output plane. And then plane A has its own little grid of weights, right, that connects each unit in the input to this one unit in the output, okay? So that's kind of how we talk about sliding this grid of weights across here, right? Because we can kind of think of it, right, as being, that's how we can think of the receptive fields as being arranged, right? Is the grid of weights applied in this location to go to this unit, and then this location to go to this unit, and then the next one over to go to this unit, right? But it's the same grid of weights. And this is what I think tripped up a lot of people, right? Because these are, in this example, kernels, right? When I started talking about these things, I described them as filters, but when I finished talking about this, I was calling them kernels, and that change in terminology tripped a bunch of people up. And again, that's not just me being, I'd like to think, that's not just me being an idiot. The problem is that's how they're usually talked about in the literature, right? Is people call them kernels even when that's technically wrong and it gets confusing, right? So in TensorFlow terminology, the little grid of weights is most properly called a kernel, right? When we're doing this, so when we arrange it this way, when we're sort of pattern matching for this grid of weights, right? Okay, again, I need to be precise. What we can kind of think of this as is pattern matching, where a pattern is defined by the kernel, right? By this little grid of weights. And if we're doing that, if we're applying the same grid of weights here, and then sliding over a little bit and doing it again, and then sliding over a little bit and doing it again, right? That looks a lot like a convolution. That is not identical to, but similar, right, to the mathematical concept of a convolution. Hence the name of the network, right? And when we do that, we can kind of think of what we're doing as looking for a feature, or filter, right, in a convolution, right? In a convolution, the pattern you're looking for can be called a, what the hell just happened? Can be called a feature or a filter, right? So that's where those terms come from, okay? And again, there's a little bit of confusion. Stop it. Whoop. There we go. There's a little bit of confusion, right? Because feature and filter are sometimes used interchangeably and sometimes used to mean different things, okay? If we're viewing this like as a Convo-Layer, and if we're doing the weight tying, then these output planes become feature maps or feature planes, right? And we can interpret them as how much the receptive field at this location matched the feature defined by this kernel, okay? Well, I should say the receptive field at each location in the input plane matched that plane's kernel, okay? So the behavior of every kernel applied to every plane is added together, right? Added to get the location in the feature map, all right? So what that means is, and I'm very out of room to write, right? What that means is feature planes contain many kernels, okay? A feature is the result of combining different kernels. Each input plane gets its own kernel, its own weight pattern inside of the feature, okay? And again, I think that switch in terminology is one thing that just really stumbled a bunch of people, okay? So, I think, hopefully, I hope this has helped and not hurt, right? I've tried to go through and be slow. I may have stumbled a couple of times. I've tried to use my terms very carefully. I really hope that helps, all right? So if you're with me so far, I'm about to erase this, right? So hit, well, maybe I can hit screen cap. I hope that worked, right? So, right, if you're with me so far, that means, right, I'm going to condense this a little bit, right? Again, I apologize that I cannot draw a perspective square. It's difficult when you're sitting at an angle. And it's difficult when it's just a dumb tablet and it's on one of those little Cintiq things that shows the stuff you're drawing. All right. Right? So, if we have our little... I'm going to try to get this in the same colors as much as I can. I apologize for nothing as far as these not being straight lines. That's just the nature of me. All right. And we got kernel A for plane A and kernel B for filter B, right? Or for plane B, right? So plane B, plane A has okay, sorry. So plane A and plane B still have kernel A and kernel B that goes to output plane A, right? Or filter map A. And again, I'm very sorry, there's just a lot of different terms and concepts to keep track of. I'm doing the best I can, but it is sort of the nature of the beast, right? If you've got me so far, right? And if you like thinking about filters, what we can sort of think about, right, is a layer that has, so if we look at this layer, okay, the weights in these kernels plus whatever the activation is, right? Right? Because remember, they do go through an activation, all right? We can think of that as a layer, a Convo-Layer with 3 filters / feature maps / feature planes, right? That each have 2 kernels, right? One that goes to each input, okay? So one Convo-Layer with 3 filters, right, that produce 3 feature maps or feature planes, and that each use 2 kernels because there are 2 inputs, okay? So how many kernels do we have? If we've got 3 filters and each filter has 2 kernels, then we have 6, right? So we're learning 6 of these little grids, right? Where each grid maps 1 input plane to 1 output plane, right? Hopefully, we are all more or less okay at this point, because again, I know that this was very confusing, I think, to some people, and the random shifts in terminology don't help, right? And I think a good intuition to have, right, is to think of it like a convolution where each of the filter maps, right, each filter map / output plane / feature plane / whatever, right, each output plane, loosely speaking, is looking in each of the input planes for a feature, right? And every location in the output plane is how much the input matched that feature, right? I think that's a good thing to grab onto if you're still kind of overwhelmed and struggling, all right? Whew. Oh, right, and the thing that I wanted to draw on this page, right, is that kind of concept of, wrong color, right, sort of illustrating the relationship of feature maps to filters, right? Each filter or feature has multiple kernels, right? Why is that? Is that good, right? Where the little weight patterns in TensorFlow terminology are the kernels, right? Each feature has multiple kernels, one kernel per input plane, right? So filter, feature, output plane has multiple kernels, one per input plane. Okay? And again, I'm going to say again, if you're still pretty confused, you're not wrong. I think a lot of people, it's normal to take time to wrap your head around this, and it's going to be more normal if you haven't had a digital signal processing class and you don't have an intuition for what a convolution is supposed to be, right? So it's really going to be a boggle for a little bit, and that's, I guess, okay, what I'm trying to say is don't be worried, right, if you're still kind of confused, because it's normal to be confused at this point, and I'm not sure there's much of a right or way to talk about these things that wouldn't do that. It just takes some time to wrap your head around, all right? So I hope this explainer has helped. You know, get a cup of coffee, watch it at half speed, you know, pause it, and if you're comfortable with the stuff on this slide on this screen, you're probably good. Okay? So, I'm going to go ahead and put, may as well leave that up. I'm going to go ahead and put that up. I'm going to go off and do some RNN slides, and then we'll talk about RNNs and LSTMs, and that'll be the second half of the week's, like, Unit 7, Unit 8 lecture. All right.